a video about Meltdown attack. So, what is Meltdown attack? Meltdown is the hardware vulnerabilities in the design of modern processors, especially in the Intel's CPU. As the name suggests, this attack melts down the security boundaries that has been enforced by the hardware. So when it attacks, it will allow user-level programs to read data stored inside the kernel memory. This is the operating system where kernel is operating here. So it causes leaking of memory that contains include personal or sensitive data like password, photos, or even message. So who is affected? So yes, obviously, desktop, laptop, and cloud computer. Well, technically on every Intel processor. So, for this project objective is first, to understand the basic concept of a meltdown. Second, to discuss and explain on meltdown attack. Third, to conduct first-hand experience of meltdown attack on personal computer. So, this is for the procedures. Let's start with our first-hand experience of conducting this meltdown attack on our laptop. So, from the task 1 is reading from cache versus from memory. Meltdown attack uses CPU cache to steal the protected secret. It's because cache memory provides data to the high-speed processor at a faster speed compared to main memory. In this task, a threshold that can be used to distinguish these two types of memory access, accessing data from the cache versus accessing data from the main memory is found. So we use the 8D. The following code using the cc -marsh equal to native cache time.c and is compiled and ran. The access of array 3 multiplied by 4009c and 7 array, then other of element is observed. For the task 2, we are using cache as a side channel. In this objective of this task is to create side channel attack called flash reload to extract a secret value used by the victim function. So the entire array from the cache memory is flushed to make sure the array is not cached. The victim function is invoked with access one of the array elements based on the value of the secrets. This action causes the corresponding array element to be cached. The entire array is reloaded, and the time it takes to reload each element is measured. If one specific element's loading time is fast, it is very likely the element is already in the cache. This element must be the one accessed by the victim function. Therefore, the secret value can be figured. So here is currently 94. So this is the secret data. So for task 4 is the access kernel memory from user space. This experiment is done to see whether we can directly get the secret from this address or not. This program is compiled, ran, and observed. So right now is our secret data address is F9EA500. So right now we are compiling the new which segmentation fault, which means it is correct. Task 5 is we are seeing the handling error or exception in C, where we are accessing the kernel memory from the user space will cause the program to crash due to memory violation. Therefore, we need to provide an exception handling so that the program can continue to execute. Our own signal handler is defined in the program to capture the exception raised by catastrophic event by using the C program provided. So for task C is out of order execution by CPU. So instead of executing the instruction strictly in their original order, the high performance CPU allows out of order execution to exhaust all of the execution units. With this feature, CPU can run ahead once the required resources are available. Unfortunately, results of the execution will not be committed before the access check finishes. If it fails, then the results are discarded. However, the reference memory is fetched into a register and also stored in the cache and create an observable effect. This side channel code implemented in task 1 and 2 is used to check whether the effect caused by an out of order execution can be observed. So for the task 7 is the naive approach. Although we can observe that effect, we do not get any useful information about the secrets. This approach, as in the lab manual, is tried by modifying Meltdown experiment in C, and the result is observed whether it fails or succeeds. So task 7.2 is we are improving the attack by getting the secret data cache. If the kernel data is already in the CPU cache, loading the kernel data into a register will be much faster. We can get to our critical instruction before the fail check aborts our out of order execution. Therefore, the kernel secret data is cached before launching the attack. This user level program is used to invoke a function inside the kernel module that will access the secret data without leaking it to the user level program. The modified attack program is ran, and the success rate is observed whether it improves or not. For task 7.3 is using assembly code to trigger Meltdown. We can improve the attack success rate by adding a few lines of assembly instruction before the kernel memory access, as Meltdown _ASM function was called. This code basically does useless computation, but according to a post discussion, these extra lines of code give the algorithmic unit something to chew while memory access is being circulated. For the task 8 is make the attack more practical. Sometimes our attack produces the correct secret value, but sometimes our attack fails to identify any value or identify a wrong value. To improve the accuracy, a statistical technique is used by creating a score array of size 256. One element for each possible secret value. The attack is ran for multiple times, as it is much more reliable estimation than the one based on a single run. So the revised Meltdown.attack.c code is ran and observed. The code is modified to get all the 8 bytes of the secrets instead of 1 byte. So as the result, the 964 is the highest number of the secret value, which hits by this number, and this number was used to decrypt the private message.